이번 시간에 한 거를 이제 잠깐 복습을 해보면은 Okay, so this is the English class, but every start of the section, so I will give the brief review for the previous sections, but it's already covered in the in English in the last section, so I want to give a review in Korean, so in order to help you the learning. Is it okay? Okay. So, 그러니까 저번 시간에, 그러니까 제가 한글로 잠깐 저번 시간에 한 거를 복습을 하면요. 우리가 그러니까 확률이라는 거를 배웠는데, 네, 가장 중요한 그림이 더 위로 올라가서, 더 밑으로 가서, 요 그림이 이제 가장 중요한 건데요. 네, 이거 확률이라는 게 뭐냐 하면은, 우리가 어떤 실험을 해요. 실험을 하는 걸 이제 익스퍼리먼트라고 그러죠. 그리고 실험을 했을 때 나올 수 있는 모든 아웃컴의 셋을 우리가 샘플 스페이스. 그래서 그 샘플 스페이스가 있고 그 샘플 스페이스의 일부분, 그러니까 나올 수 있는 어떠한 아웃컴, 실험을 통해서 어떠한 아웃컴을 우리가 이벤트라고 그러죠. 그래서 이벤트는 샘플 스페이스에 서브스티트 된다. 그래서 확률이라는 거는 이러한 어떠한 이벤트를 우리가 실수 공간에 맵핑을 시키는 함수를 우리가 확률이라고 한다. 그러니까 함수니까 이 이벤트를 아규먼트로 하는 어떠한 함수가 되는 거죠. 그래서 이 실수 공간에 맵핑을 시키는데 그 프라이오리티 오브 그러니까 액션에 의해 가지고 이 실수 공간은 0에서 1 사이가 된다. 그래서 S probability of S 그러니까 전체 샘플 스페이스는 액션에 의해서 1이 되고 만약에 null 스페이스는 0이 된다. 그렇죠? 그리고 비스토릭한 게 있으면 두 개 그냥 더한 게 된다. 라는 거고요. 그래서 그게 확률의 개념이다. 그리고 그 다음에 이제 우리가 컨디셔널 프로버빌리티에 대해서 이제 잠깐 이야기했는데 오늘 이제 본격적으로 컨디셔널 프로버빌리티에 대해서 이야기를 해보도록 하겠습니다. Okay, so in this session, so we're gonna discuss about the more about the conditional probability. Conditional probability is written like it's notated by so this is the probability A. That means probability of the event A. But conditional probability is probability in A given B. That means we assume that B is already occurs. So here, this is the probability of A. That means A might occur or not. However, in this case, probability B is already occurred, so it's already determined. And in that condition, what's the probability that A gonna be occur or not? That is a conditional probability. So, by definition, it is calculated by probability that A and B occurs together divided by probability of B itself. So in this, the Venn diagram. Okay, so here, this one we call conditional probability. And in contrast to the conditional probability, we call this one without condition is a marginal. So we call this is the usual probability as a marginal probability, and this one is conditional probability. So it does what we are saying. So here, if you think about the concept of this conditional probability, here is A and here is B. Okay? So the conditional probability means B is already occurs. That means it is only defined within this B. And in that condition, what's the probability of A occurs? That means this one. Right? So virtually, this conditional probability thing, this B whole B is a virtual sample space, right? That's why probability of B given B is, what would it be? It's 1. Because we know B is already occurred, right? And what is the probability that B gonna occur? That is 1, because B is already occurred, right? So it is 1. That means it is very similar to the probability of S equal to 1, because S is a sample space. That's why I'm saying B is virtually sample space in the conditional probability. Okay. So within this one, so what's the probability that A gonna occur? That is this part. That A and B gonna occur together. Then what's the relative probability of this one among this one? That is calculated by this, right? Probability that A and B occurs together divided by probability of B. So this is the concept. So because this B given B is considered as a virtual sample space, so everything is the same. Every probability action is also hold. For example, any event of A given B should be non-negative between 1 and 0, definitely. Then probability of B given B is 1. And any disjoint event, A1, A2, AN, it is given in this way. That means this is A1, and if there is the A2 disjoint event like this, it's the same. So everything is the same. A3. So if they have no intersection, then they don't need to hold. So it's nothing difficult, right? Okay, so let's look at some examples. So could you go over to the example? Okay, so this example. Okay, so let's consider two pair four-sided dice. Do you know what's a four-sided dice? Usually our dice is six-sided dice. But four-sided dice is, because I'm not that good for the drawing. This is the four-sided dice. So each face is a triangle. And it has 1, 2, 4. Is there any the five-sided dice? Five-sided dice would be possible? What do you think? We might have five-sided dice. Can you do it?
Oh, you could have like a pyramid with four sides.
Four-sided and one face. But there's another side.
But it would be a pyramid.
It's a pyramid.
Yeah.
Oh, okay. Oh, yeah.
Side.
Yeah, a pyramid like this.
Yeah.
Okay, so this is the five-sided dice. Okay, it is a five-sided dice. Oh, okay, so let me change the question. Is it possible to make the fair five-sided dice? Fair. Fair means, so the probability that they're showing each side should be equal. Right. So the fair five-sided dice is not possible. So for fair four-sided dice like this is possible because every face has the same one. However, imaginary, you can imagine the fair five-sided dice. Imagine, right? Even though it's not possible during the it's not possible in the real world. However, okay, so let's consider this a four-sided dice. Then x1 and x2 denote the number of dots or number of numbers on the face of these dice. And okay, let's look at the x1, only x1. What's the sample space of the x1? What's the sample space of the x1? 1, 2, 3, 4. Right? So S of x1 gonna be 1, 2, 3, 4. How about x2? Same 1, 2, 3, 4. Then if we roll these two dice together, what's gonna be the sample space? There are gonna be there's a set with 16 elements. You got it? You guys following me? 자, 여러분, 그 4면짜리 주사위 던지면은 아웃컴이 총 몇 개 나오죠? 16개. 맞아요? 네. 뒤에 분들. Okay, then, we can actually present the sample space in this coordinate. So, x-axis is the outcome of x1, y-axis is the outcome of x2. Then, total our sample space is gonna be 1, 2, 3, 4. And here is 1, 2, 3, 4. So 1 by 1 and 1 by 2, 1 by 3, 1 by 4, blah blah blah. In total, 16 points, like this. Okay? So this is our sample space. Then let's consider event A is the event that x1 is larger than or equal to 2. Then what's the event A? x1 should be larger than or equal to 2. That is, A is, this one is A. Am I right? Then what's the probability of A? Three over 4, or 9 over 16. Drive over 16. Drive over 16. And how about the B? What's the B? Event B. Event B is x2 should be larger than x1. Abdullah? Can you write the event B? Can you mark what's the event B in here? Come on. Well, what's the area for the event B? Yes, so x2 should be larger than x1. No, x2 is larger than x1. Something like, can you have it? So when x1 is 1, it should be starting from 2. 2, 3, 4 is the x. Yeah, that's right. Triangle that includes some little code. Okay, so could you help it? Could you help your friend? Right. So this, the blue triangle represents the event that x2 is larger than x1. So this event is with B. Abdullah, what's the probability of B? Four. What's the probability of this B? That means what's the probability that you're gonna see this 1, 2, 3, 4, 5, 6 outcomes among the whole possible outcomes?
6 over 16.
6 over 16. Yes. Probability B is 6 over 16. Okay, good job. Then our final question is what's the probability that A given B? What's the probability of A given B? What do you think? A given B means B is already occurs, right? Then what's the probability that A gonna occur too? Pardon? 3 out of 6, right? 3 out of 6. The reason is the number of the event B is 1, 2, 3, 4, 5, 6 because B is already occurs. Then the probability that A is only this 3. That's why 3 over 16. How about this? How about the probability that B given A? B given A. 자, B 기분 A 뭘까요? 3 over 12. Yes, that's right. This is the whole A, and this is something commonly occur. So 3 over 12. Okay? So this is the basic concept of the conditional probability. Easy? Easy. Okay. Then let's a little bit discuss about the law of total probability. The name is quite fancy, but it's actually nothing. So let's think about whole sample space S, and let's consider that this S can be the partition into the several other space, other events like B1, B2, B3, B4. Like this going to be there. That means B1, B2, B3, B4 is this joint. That means there's no intersection. However, if we add all of these B's, then it is equal to X. That means X is partitioned into the several sub-regions, like B1 to B. Let's say in general in M, Bn, B1 to Bn. So B1 to Bn, small n. Then S. So B1, B2, B3, let's say B until B4. And there is an event A. Okay? Then technically this A is sum of this jointed set of this one and this one and this one and this one. Technically. And this one is probability that, given as the probability that A and B1 together. So this is the set of events that A and B1 occur together. And similarly, this one is A and B2, A and B3, A and B4. Right? So, by this conditional probability, the definition of the conditional probability is probability of A given, let's say BI is, by the definition, probability that A and BI occur together divided by probability of BI. That means probability that A and BI occurs together is conditional probability times marginal probability of BI. It's a simple mathematics. It's a elementary school level of mathematics. So probability of A is definitely sum of probability of A and BI, right? It's the sum of this part, and this part, this part. And this one is, if we use this notation, then it is like this. So this is the law of the total probability. If any disjoint event B1 to Bm, any probability for A can be presented as sum of the conditional probability times marginal probability of B. That's the law of total probability. That's a very obvious thing. Even though the name of the law is very fancy, but it's actually nothing. But why it's important? Because in our real application, they don't need the very. So even though you haven't notice, you already use this law of total probability. Let's think about this simple example. Let's assume that 20% of Korean and 10% of Chinese and 5% of Japanese are handsome. Is it right? Do you agree? Thank you very much. Thank you very much. And also assume that population of Korea and China and Japan is 1.1 billion and 1.3 billion and 0.2 billion respectively. It's almost roughly true. Then what's the probability of the handsome in East Asia? What's the probability of handsome in East Asia? When you see a guy in East Asia guy, then what's the probability that that guy is going to be handsome? So this is the very simple problem, and this is you can see the similar problems in the real world so many times. Okay, so let's consider so we are only talking about the East Asia. So the East Asia is our sample space. Whole sample space is the East Asia. And we are interested in the probability of handsome. So men or the boys or girls are separated into handsome and non-handsome. Handsome. Let me check. I'm handsome. How many? I'm handsome. Please, can you raise your hand? 1, 2, 3, 4. Including me. Much less than 20%. Much less than 20%, but that's okay. Anyway, so in East Asia, we are interested in the handsomes. How many handsome? But this when you usually say the East Asia, it's only concerning the 3 countries, right? Usually, yes, maybe the more countries, but usually we say 3 countries. So this East Asia can be partitioned into the 3 parts, disjointed part, like Korea, China, and Japan. definitely someone is the both Korean and Chinese, but let's ignore the such a case for this one. So if we want to calculate handsome by using the law of total, we can calculate probability of handsome is probability of handsome in Korea plus probability of handsome in China plus probability of handsome in Japan. However, our information doesn't say this one is directly. What we know is the probability of the handsome probability of Koreans. That means if a guy is a Korean, if that condition is satisfied, the probability to be handsome is 20%. That means it's a conditional probability. You got it? It's a conditional probability. It's not the HK itself. So we rewrite this example like probability of handsome given Korean. If a guy is Korean, also probability handsome. That is given in the problem. It times probability of Korea. How can you calculate this probability of Korea in the East Asia? Because we know the total populations, so roughly, it's the proportional to the total population, right? So similarly, this one is the plus probability of handsome in China times probability of China plus probability of handsome in Japan times probability of Japan. So these probabilities, probability of handsome in Korea, it's already given. It's how much? 20%, 0.2. How about this one? Probability of Korean. What's the probability of the probability of Korean? That means if it 1 over 16. Yes. And this one is 10%, 0.1. And probability of Chinese is 13 over 16. And this one is 0.05. And this one is 2 over 16. Then if you calculate this one, you can get the probability of handsome in East Asia. So this is a typical example to use law of total probability. Actually, without knowing the law of probability, you can solve out this problem because intuitively you already know this law of total probability. You got it? 자, 여러분 이해하셨어요? law of total probability. 네, 아무것도 아니에요, 사실. 네. 사실 그냥 여러분이 직관적으로 알 수 있는 거를 네, 멋있게 말을 통해서 네, 다시 풀어쓴 것 뿐입니다. 아무것도 아니에요. 진짜 알겠어요? 모르는데 알겠다 그럽니다. 네, 이게 지금 어려운 거 하고 있는 게 아니죠. 네, 중학교 수준을 하고 있습니다. 그래서 다음에 좀 더 멋있는 걸 해볼게요. Okay, so the next one is Bayes' theorem. Bayes' theorem. The theorem is, the very weird. Very fancy names, and but this is actually nothing. This Bayes' theorem is nothing actually. So Bayes, here is a quick question. It is who first invented this Bayes' theorem? Bayes. Yes, that's why it's a Bayes' theorem. This Bayes' theorem is the very the fundamental stuff in the probability. So if you learn more about the artificial intelligence, like 인공지능, so the very famous application is, or the theory is Bayesian network. So you may heard about some AI or the neural network 신경망 or artificial neural network 인공신경망 or the deep learning, deep neural network, blah blah blah. So before the neural network is very famous or getting popular. One of the most popular thing is is a Bayesian network. Bayesian network is also used very well in this area. So this Bayesian is this way. So this is the fundamental stuff in the artificial intelligence. What's the Bayes theorem? Bayes theorem itself is saying probability of P given A is equal to probability of A given B divided by times probability of P divided by probability of A. This is a Bayes theorem. Right? Yes. And it is very obvious. You can easily prove it, right? It is very obvious. So by its definition, by the definition of this one, probability, this is equal to probability of B and A together divided by probability of A. And this one can be rewrite in this way by the definition of the probability A given B. So it is very obvious. So that you can easily prove it. So it's very obvious, right? 여러분 이거 수식이 이렇게 당연히 나오는 거 아시겠어요? 네, 뒤에 분 모자 쓴 학생 알겠어요? 이렇게 당연히 나오는 거? 네, 그냥 그 컨디셔널 프로버빌리티 정의를 이렇게 좀 바꿔서 넣으면 돼요. 네. So here, why this one is the important? The reason is, in many cases, we want to know probability of B given A. However, our information is given with this one, probability of A given B. So, it is important to getting probability B given A from the given information of probability of A given B. Okay, so let's consider this example. It's the same example. Let's assume that 20% of Korean and 10% of Chinese and 5% of Japanese are handsome, and also assume that population is the same, 0.1 billion and 0.3 billion and 0.2 billion respectively. Okay, this is the same condition from the previous example. Then, you don't have to, but here, if we interested in, okay, what's the probability that a handsome guy is Korean? That means our interest is what's the probability that we know that guy is handsome, right? And I want to know what's the probability that that guy is Korean. That means Korean even handsome. Sometimes we are interested in this probability. Why? You don't have to calculate this probability at this moment, but in my case, when I study in the US, sometimes I saw the very pretty girls, and I'm interested. That girl gonna be Korean or Japanese or Chinese. That's important, right? If she is Korean, that's much easier to get together. But so such the probability is quite important in that situations, right? Do you agree? Yeah, you guys might agree. So how can you calculate this one? But in this problem, this information is not given. So how can you calculate this? One can calculate probability that by this Bayes theorem, handsome given Korean times probability of Korean divided by probability of handsome. Right? So this information, handsome given Korean, is given in the problem at the 20%, and probability of Korean is 1/16. It's given in problem, and probability handsome we already calculated using the law of total probability. So we can calculate this one. Okay. So the Bayes theorem is quite important in many cases, especially we use this Bayes theorem to obtain the hard to have information from easy to have information. For example, so another or the more practical example is let's think about the occurrence probability of a heart attack probability. So every country report what's the something similar to the something similar information about your heart attack probability. Every country reports it annually. So that means the heart attack probability in Korea and China and Japan are easy to get. That information is easy to get. However, if you share the heart attack to man, and if we want to calculate what's the probability that that guy is a Korean or Japanese or Chinese, that kind of information is not given in general. But sometimes it is important to text this guy to the hospitals or getting some insurance information. So nationality is sometimes very important, right? But that kind of information is cannot be obtained from the just using the raw information. However, using this Bayes theorem, we can calculate it. That's why we use this Bayes theorem. So the Bayes theorem can be, using the law of total probability, we can rewrite it in this form. So this probability A, using the law of total probability, if it has a disjointed B1 to Bm, we can rewrite in this way. So that means if we know A given Bi, and this, the probability of the Bi given A can be totally presented by A given Bi and the probability of Bi. So in this case, this probability of handsome can be rewrite probability of handsome given Korean, probability time from Korean, plus probability of handsome in China, probability of China, plus handsome in Japan. We can rewrite this one in this way, right? So in this case, K given H can be totally calculated from H given K or H given C and the probability of the Korean, Chinese, and Japan. So this is the Bayes theorem. You got it? 자, 여러분 아시겠나요? 네, 이게 바로 베이즈 티어입니다. 보기에는 아무것도 아닌데요. 나중에 이걸 실제로 적용하려면 좀 헷갈려요. 네, 실제로 적용하려면 좀 헷갈립니다. 그래서 문제 좀 더 확대할 수 있나? 조기만 또 문제도 확대해볼래? 자, 지금부터 얼마 드리면 되나? 5분 드릴 테니까 저 문제 한번 풀어보세요. Okay, so I'll give you 5 minutes. Please think about it. Check this problem. I think the first problem is relatively easy. What's the probability of the acceptable register? It's easy. And what's the second probability? Second question. Second question is a little bit It's also easy, but you need to do more calculation. So the acceptable probability that acceptable register comes from the machine. 그리고 그 엔지니어링 이 과목이 수학 과목이긴 하지만 엔지니어링의 특성상 근데 고학도의 특성상 소수점 둘째 자리까지만 맞으면 맞는 거예요. 무슨 말인지 아나요? 10%의 에러는 문과로 진짜 다 중앙의 특성상 우리 정확하게 계산 안 해서도 됩니다. Okay, so I think the many students already solved this problem. So let's see this problem. So let's understand this problem. Okay, we have three machines, B1, B2, B3, and they make registers. And there's some bad registers and good registers. And the probability of the making good registers or acceptable registers is B1 is 80%, and B2 is 90%, and B3 case, it's a really bad machine, so it only produces 60%. Okay? And in this factory, B1 makes 3,000 registers, let's say for each hour or each day, whatever, at the unit time, and B2 makes 4,000 and B3 makes 3,000. Then in here, our question is, what's the probability of the acceptable registers? That's the probability. So let's model this problem with probability. Okay. So here we are interested in probability of acceptable registers, PA, right? Then the given what's the given information? The given information is the probability of acceptable registers when in the condition that that register made by this machine B, that is 80%. So here what we know is A given B1. So if it's made in B1, what's the probability of acceptance? That's 8%, 0.8. Similarly, we know probability of A given B2, 2 is 0.9, probability of A even B3 is 0.6. And we also know the probability, okay, so when we pick a register, we also know the probability that that register comes from the B1, right? The probability of the B1. Because we know the total population. So the population or the relative ratios of the generations making these registers, right? So what's the probability of B1? What's the probability of B1? 0.3, because we add all of the total number of the registers. That's 10,000. Among 10,000, B1 makes 3,000. So it's a 0.3. Similarly, probability of B2 is 0.4. Probability of B3 is also 0.3. Here, we are interested in A. Typically, register should be made by one of these B1 or B2 or B3. That means B1, B2, B3 are disjoint event. So we can rewrite this one, probability of, by the law of total probability. Let's use probability of A given B1 and probability of B1 plus probability of A given B2, probability of B2 plus probability of A given B3, probability of B3. And we know all of these probabilities. Then if you're doing simple mathematics, what's the result? The answer is 0.78. Okay. So the answer of the first question is 0.78. Then second question, what's the probability that an acceptable register comes from the B3? That means we know, okay, this register is the accepted registers. Then what's the probability that that register is made by these three? That is, we want to calculate probability of B3 given A. But this information is not given in the program. So we have to calculate this one from the known information. How to? Using Bayes theorem. Right? So this one is probability of A given B3 and probability of B3 divided by probability of A. We know this one, we know this, and we already calculated the probability A. So, doing some simple mathematics, what's the answer? 0.23. Okay. Thank you. Actually, during I preparing this the lecture, I haven't calculated the actual number. I just write down the equations, and now I know the answer. Answer is 0.23. Okay, thank you. It's easy, right? So nothing difficult. Okay, so then the next discuss about the next concept, independence. Independence. Okay, so let's think about the two events, A and B. We say A and B are independent if and only if probability that A and B occurs together is equal to probability of A times probability of B. If this relationship is whole, then we say A and B are independent. This is the definition of independence. Or we say A, using using this notation, we say independence. B, A is independent, A and B are independent using this notation. If and only if probability that A and B occurs together is equal to A and probability of B. This independency can be interpreted in this way. First one, two events has no relation at all. For example, so when we the flipping a coin. Okay, so let's think of so we are doing the rolling a dice, and what's the probability that we get 1 and 1? First outcome is the first outcome of the first dice is 1, and the outcome of the second dice is 1. What's the probability of that one? 1/36. That means probability of 1, 1 is equal to probability of 1 times probability of 1. Because this one is 1/6, this is 1/36. That means the outcome of the first dice and the second dice, they have nothing to do with it. They are totally independent. That means, or you can also think, knowing the outcome of the one event doesn't help at all to predict the outcome of the other one. That means, okay, so let's think about we know the outcome of the first dice, but that doesn't help to predict the outcome of the second dice. Am I right? In that case, two events are independent. So how about this? How about our favorite example with the handsomeness example? Let's think about the two events: handsome event and another event, Korean. Are they independent to each other? No, because if we know, okay, if this guy is Korean, then the handsomeness probability is increased. Right? That means knowing nationality actually helps to predict whether this guy is the handsome or not. That means two events is not independent. So mathematically, when we calculate the probability of conditional probability A given B, is if A and B are independent, by definition, this is the probability of A, B, A and B occur together, divided by probability of B. If A and B are independent, by its definition, this is the probability of A times probability of B, divided by probability of B, and this one is removed. So this is simply probability of A. So if A and B are independent to each other, the conditional probability is equal to the marginal probability of A. Okay? That means knowing the result of B doesn't help to predict result of A, because whether the B occur or not, it has the probability is the same. So it doesn't help. So that's actually the interpretation for the second one. Okay. This is so if you want to check whether the two events are independent or not, mathematically you can check whether this joint probability, this one, A and B occur together, is equal to the multiplication of the two marginal probability. Or intuitively, you can think whether two events are related to each other, or you can think you can check if I know the result of one event, whether it's gonna be held the other ones. Okay, next one. So in general, so we can define the independence among the n events, among n events. So if we check the independence of define the independence of the three events, that is A1 and A2 are independent to each other, and A2 and A3 are independent to each other, and A3 and A1 should be independent to each other. So every the two pairs, so every pair should be independent to each other. Okay, and also the probability that A1, A2, A3 are occur together should be equal to the product of the A1, A2, A3, each probability. If these four conditions is hold, then we say these three events, A1, A2, A3, are independent to each other. And in general, we can define these events for the independence for the n events. One condition, recursively. That means for n events, so every set of n minus 1 events, so that if we choose any among n events, if we choose any set of the n minus 1 event, that one should be independent. Like this. So that this one is every pair of the two events are independent. And also probability of the n events occur together should be equal to the product of each marginal probability. So in this case, we say the n events are independent. So the independence of the n events are defined by independence of the n minus 1 event, right? So how we can define the n minus 1 events independently? Using the n minus 2 events independence, and recursively it goes up to the independence of the two events, and two events are here defined here. So we can in general define any independence. Okay, so the anniversary, the marriage anniversary, 결혼기념일 is July 1st. Do you know what's July 1st? This is the Independence Day of the United States. What we call this is our Independence Day. So anyway, 여러분 네 조커였어요. 네 별로 안 좋은 것 같아요. 네 Independence Day. 네 어쨌든 네 수고하셨고요. 여기 다음에 문제 하나 있는데, okay, so we have some example of the independence. So please check by yourself. Okay? 자 여러분 네 수고하셨습니다. 여러분 여기 갈게요. 네.